Section 3.3, we're going to take a look at increasing and decreasing functions and the first derivative test. So the first thing we're going to talk about is what we mean by increasing and decreasing from a analytical point of view, sort of an equation point of view. An interval on which a function is increasing will have the condition that when x1 is less than x2, f of x1 is less than f of x2. So what does that look like visually? Well, along the x-axis, if the x1 value is before the x2 value, that's what this is referencing. It's telling you that the y value corresponding to the x1 value, this is f of x1, lies below the y value corresponding to the x2 value. This is f of x2. And somehow these are connected. They can be connected in whatever way you'd like, but the idea is that one is higher than the other. Okay, that's increasing. And as always, we're reading graphs from left to right, just like we read English from left to right. So if we're sort of thinking about it from that perspective, you would have looked at this graph and you would have told me it was increasing anyway, right? All right, decreasing. This is an interval on which a function has the condition that if x1 is less than x2, so they're the same order on the x-axis, then f of x1 is greater than f of x2.
So it's basically the same graph, just opposite.
Right. So x1 and x2 are in roughly, if you will, the same correspondence, right? Same locations. But the x1's y value up here, so this is f of x1, needs to be higher than, larger than, bigger than the x2's y value, f of x2. Okay, so it looks maybe like this. Right? Again, reading from left to right, you guys would definitely say, yes, I can sled down that hill, or something like that, right? This is a decreasing graph. All right, so think about with me then, if you were to graph tangent lines on curves like this. Okay? So if I were to graph a tangent line to this curve, say like right here, and you guys know how to graph tangent lines, it would look something like this, right? And if I were to do a tangent line on this curve down here, it would look something like this. Tell me what you can say about the slope of the first line, the top one.
Positive.
It's positive. The slope is positive on the first one, right? Don't use words increasing, decreasing, because with lines, slopes are constant. There's no increasing and decreasing here on the slopes. The slopes are positive or negative. So this graph has a slope that's positive. And this graph, the second one, what can you say about its slope? The slope is negative. Now that relationship is not a coincidence, and it happens all the time. If the graph is increasing, you're going to get derivatives or tangent lines that are positive. And if the graph is decreasing, you're going to get derivatives or tangent lines that have slopes that are negative.
Is that like the related rates pushing down?
Very similar, yeah. So this theorem actually tells us that if we have a positive derivative, that's what this is saying, if the derivative, f prime of x, is greater than 0, is positive, then the function itself is increasing. And if the derivative is negative, then the function itself is decreasing.
Can we just put the negative?
Yeah, if you want to, you can write the words negative and positive. That's fine. And if the derivative is equal to 0, then it is constant. And that's on an interval. Notice that's saying on an interval, not at a specific point. If it's 0 at a specific point, we already saw what happens with that potentially anyway as maximum and minimums back in section 1. Okay, but if it's constantly 0, if it's 0 the entire interval, then it would be a constant graph or flat, like a flat graph, a horizontal line. So this isn't the first derivative test, but it gives us a lot of information about the graphs themselves. But the first derivative test is related. It talks about what happens as the slopes of these tangent lines change. And this is the one where you have tons of writing. So let me let you write it all in first, and then I'll read through what it is and talk about it, okay? So write in all the words and all the functions and everything there, and then we'll chat. So there are 3 parts to this theorem, right? They're numbered. The first one says if the derivative is positive, well, let me actually go back to the conditions at the beginning just to specify first. We have an interval a to b, and we have a point c that's somewhere in between. Okay, so our interval goes a, c, b. That's what it looks like numerically across. So if we're looking at the ordering here, we've got a, and then c, and then b. They don't necessarily have to be spaced evenly apart, but this is what the ordering looks like. So the first condition here says that if we have a graph that goes with a derivative that's positive, and then it changes to a derivative that's negative. Well, if the derivative is positive, it means the graph is increasing. That's what the last theorem said. So if the derivative is positive, the graph is increasing. And then the derivative is negative after that, the graph is decreasing. As long as the interval that we're looking at had a function that was continuous on it, what would have to happen between the increasing and the decreasing parts? We'd have to have a maximum there. You guys see that? So this point right here would be a maximum location. And it's called a local or a relative maximum. Okay, so we've encountered that phrase once before, I believe, or did we only encounter the global in the other one? I think we may have talked about it, but it wasn't put in our notes. Okay, so your book, I think, uses the word local, which is why I'm using it here, but another word that you will see used interchangeably, and I will probably use the word more frequently, is the word relative. Okay, it's a relative maximum. All right, the second condition, number 2 here, says, if I have a graph that goes from negative, a derivative that's negative, to a derivative that's positive, what happens? Well, if a derivative is negative, then the graph is decreasing. And then if the derivative is positive, then the graph would be increasing. So somewhere between those 2 spots where it changes from increasing or decreasing to increasing, we would have a minimum, right? We'd have a slope of 0. Okay? The last one says that if you have the same sign, right, if it's positive, positive, or negative, negative, then the location that they're changing at, if you will, it isn't a max or a min. Right? It's saying, like, I didn't actually find anything. And yeah, a really good example of this is the graph y equal x cubed. Yeah, you could do the graph y equal x as well. X cubed is sort of the default example because it actually has the ability to have a flat spot in the middle there, but it's increasing both on the left-hand side and it's increasing on the right-hand side. You get positive derivatives on the left, you get positive derivatives on the right. There's just this one little place right here that you have a derivative of 0. So, okay? So we're going to do some examples. I know. That's what math is, right? Lots of examples. Identify the open intervals on which the function is increasing or decreasing. All right, so the way we decide if things are increasing or decreasing is that we look at derivatives, and we find out if derivatives are positive and negative. It is a lot easier on a function, like without a graphing calculator. I get it. You've got a graphing calculator. I would encourage you to verify your results. It's a lot easier if you're working with the equations themselves to decide if a graph is positive or negative than if a graph is increasing or decreasing. So we can do that a lot quicker, all right? So this one wants us to find if it's increasing or decreasing. We do that by finding the derivative. So let's rewrite this first. And our goal is to find the derivative and to set it equal to 0. That's what we're really going to do. All right? So what is the derivative of x plus 4x to the negative 1?
Minus 4x to the negative 2.
Excellent. And if we rewrite this with positive exponents, we get this, right? Okay, so this is our derivative. That is all the calculus, manipulation anyway, that we have here. And we've done that before. There's nothing new in that particular step. We've also done the next step, which is to set it equal to 0 and solve. That's not even calculus, although we've done it recently in section 3.1. That's an algebra step. So any ideas about how we're going to do this piece? Okay, so we could do, this one would work nice enough to subtract the 1 to the right-hand side, then what? Yeah, this looks a lot like the last problem I did in the last section. Negative 4 over, or equals negative x squared.
You get imaginary number.
I don't actually get imaginary numbers. I can deal with something else before I get to that point of worrying about it.
You can divide by -1.
Yeah, I can divide both sides by -1. So instead of this being the negative 4, this is actually just the same as 4 equals x squared. So what does x equal?
2.
Oh yeah, we need the both plus or the minus. Be careful on that, plus or minus 2. Okay, everybody good with that? All right, here's what we do next. So we haven't seen this that I'm going to show you next before. We set up an interval on a number line. And the values we put, in fact, actually let me do this where I've got a little bit more space. The values we put on the number line are the places that we found for x, in order. If you don't do them in order, you're just creating yourself a problem, okay? So we've got -2 and +2 on the number line, okay? And what we want to do is we want to test the values that are in between. Now, we actually need one more place on the number line. Any idea, Dawson, why? Why do we need 0?
Well, it's directly in the middle of the other two, but I really don't know.
It's 0, yeah. It's undefined.
Yeah, the original equation that we had a continuity issue, didn't it?
Yes.
What happened at x equals 0 on that graph? It was undefined. Do you know why? There's an asymptote there, right? And if you have an asymptote, is it possible to change the direction of increasing to decreasing on an asymptote?
Yes.
Yeah, definitely a possibility. So this number line needs to include the value 0 because it's a continuity problem. So we get these interval right here, and we have to go back up to the original function and notice that x cannot equal 0. So there's an asymptote, and we have, and sometimes even if there's not an asymptote, there could be a hole, right, on something. We still have the possibility of something changing direction there, even though it doesn't have a derivative equal to 0 there. Remember, it can change these directions when the derivative is equal to 0 or does not exist, and the derivative does not exist on this one at x equals 0. All right, now we have the ability to pick numbers in between these numbers, and by all means, pick something nice. Don't pick weird stuff. I mean, make life easy.
1 and -1.
Yeah, I like -1 and 1. Those are good options. What else? What? -3. I was hearing funny fractions. That's so humorous. You guys are fantastic today. What else? And 3. Okay. We have 4 points we're going to test. Now, here's something important. Let's say, for instance, that Garrett tests 3 and Luke tests 4. Okay? They're going to get different numbers, no doubt. But they will get the same sign. And the sign is what we care about here. We don't really care about the numerical value we get. We care whether it's positive or negative. So do understand that just because you test different values than maybe I test actually doesn't matter. You're going to get the same sign. So what we're actually testing is the derivative value at these 4 locations.
Do you want us to write the number like that?
You do not have to, but I'm going to write it down at least as I'm doing it in class so that everyone remembers. 2 things, actually, Garrett. One thing I want you to remember is that you have to test it into the derivative because you've got 2 equations on the screen, and I want to make sure everybody understands where you're plugging the numbers in. And then I also want you to understand that you are, in fact, plugging them in. Like, I don't care about the signs of the 1, the -1 themselves. I care about the number I get when I plug them in. Dawson?
The bottom one, 3 instead of 2.
Oh, yes, that's probably a good thing, huh? Thank you. All right, was that what you were going to tell me too, Christian? Okay, cool. All right, so we're plugging these into the derivative, right? The derivative is what I've got on all of these.
Yes.
And we are going to find out whether they are positive or negative. So the easiest thing when you're plugging a whole bunch of values in is to grab your calculator. I mean, this is not a particularly difficult function, but especially when you have negatives and positives, it's easy to make an error. You can use any of the versions of the derivative we have. I'm kind of partial to this one, but if you want to use the one above it, you can. And I would just put it into the table. So I'd put this into y equals 1 minus 4 over x squared. And then in your table, I'd put in -3, -1, 1, and 3. Yes, the derivative.
So you can't just like plug in number.
You can. You can. I will tell you that as fantastic and wonderful as all of you people are, somebody's going to make an error on a sign at some point when you square things. It's just going to happen probably. So, you know, your calculator won't make an error on the sign if you do it in a table. So I kind of like that. And that's why I'm going to go ahead and put it here anyway, because then we can check the graph when we're done to make sure that it agrees with what we believe we have going on. So, all right, so I'm going to use -3. Whoops, let's try that again. -1, 1, and 3. And what I care about are the signs. So the first sign is positive, the second one negative, the third one negative, the fourth one positive. So as I come back over to my work, I got positive. Is that what you guys got? Okay, good. Negative, negative, positive. Yeah, that's what I have written on paper too. That's very good when your notes match what you're doing. It's awesome. Okay, so what does it mean? Well, if a graph is positive, it means it's going uphill. And if it's negative, it's going downhill. Negative going downhill, positive is uphill. That's what it means. Positive means increasing. Negative means decreasing. So you don't necessarily have to draw the picture where I drew my lines going up and down. You can if you'd like, if that helps you, if you're a visual person. You can write down the phrases INC and DEC, right? Those acronyms, or not acronyms, but abbreviations, if that's helpful to you. The question actually asked us to identify the intervals where it's increasing and decreasing. So what we're going to write down are the intervals represented by this number line. So as I'm reading the number line from left to right, what is the far most left-hand? Negative infinity, right. It's not really a value, but it's a concept, so negative infinity. And I will go all the way until -2. Okay? So the numbers I'm getting are coming from these 3 locations, not from the -3 and the -1 that I plugged in. Okay? It's not coming from the numbers I plugged in. So I've got negative infinity to -2, and what is the graph doing on that interval? It's decreasing. So if I want, in fact, I will write this at the beginning here. I'm going to write that it's decreasing. Oh, sorry. Listening too carefully. Increasing. Increasing from negative infinity to -2. Is there anywhere else that it's increasing? Yes, 2 to infinity. So you can actually put a U for union and then 2 to infinity here as well. So you can kind of group the 2 pieces together. It's increasing on both the left-hand interval and the right-hand interval. And then it is going to be decreasing where?
-2 to 2.
It's not -2 to 2 actually, but you're close. -2 to 0 and then 0 to 2. Because the graph doesn't exist as 0.
So you always have parentheses and not brackets?
Yes. And there's 2 reasons for that, Katie. One is because it actually told you open intervals in the question. So it's sort of like a reminder that it's going to be open intervals. In terms of the infinities and negative infinities, those are always parentheses. The other thing is that the definitions that we have for increasing, decreasing are all defined on intervals, right? Not at a specific point. So I'm not actually decreasing, increasing on the interval at the specific endpoint because it's actually changing at those endpoints is why. All right. Excuse me.
Why
Yes.
is it not decreasing at 0?
Because it is an asymptote at 0.
Okay, but if you took, like, if you look at the graph, you took, like, the limit of it,
Mm-hmm.
you could still find the slope at that point, right?
Let's look at the graph because that's a good question. Hang on just a second.
Never mind. I was picturing the wrong graph in my mind. I was picturing
It's okay.
the constant.
All right. So here's our graph. So oh my goodness, I've got it crooked. Here, let's try that again. So if you're taking a look, wait, I'm sorry, I've got my derivative in here.
Okay.
That's what's wrong. I need to do x minus the original graph is what I meant to put in, 4 over x. Thank you. I'll fix that. Okay, I just have the standard window set up in here at the moment. Did I get it in there right? X plus 4 over x.
Yeah,
Oh, I put a 4. Okay, well, we're one of these days we're gonna actually get the whole picture. There we go. That looks better. Okay, that matches my whole picture. So this graph is in fact increasing until we get to this location, right?
Okay.
And it's decreasing on this piece, but then it stops decreasing because there's an asymptote. It picks up decreasing, but up here, and then it increases after this.
So we're just looking for the intervals that they're doing stuff at.
Correct.
So we're looking for,
It's okay. Finish, Dawson.
is it just increasing or just?
Right.
That's not what we're looking for.
No, we're looking for the intervals where it's doing the different pieces. Yes.
And then
Chad.
we put in the derivative to get the signs, and then we look at this graph to check this.
Yes. The only point of looking in this graph is to check it, because I will guarantee you if I don't see the work that supports it in terms of calculus, you're not getting any credit.
Yeah.
Yeah.
Okay, I got it.
I mean, because you can do this point, you could do this without any information really about calculus at all, right? So we're actually using the calculus to prove a point. I mean, to prove that this is actually working for us. These relationships exist. Christian.
So like if we had y equal to x squared,
Mm-hmm.
would it be decreasing from like negative infinity to the point?
Yeah.
Or like from positive infinity to the point?
If you had y equal x squared, it would be decreasing from negative infinity to 0, and it'd be increasing from 0 to infinity.
Okay.
Yes.
What if you have a hole? Could you then be decreasing through it?
Decreasing through the whole, no, because you can't decrease through something that doesn't exist for the function itself. You would still have a place where you'd have to be an open interval and leave out that point. Yeah.
So it doesn't matter like if you find like a, because if there's a hole you can still find like the limit of it.
You could still find the limit, but it's not
It doesn't work-
continuous.
It doesn't work for.
Right. The definitions that we're using all hinge on being continuous. And if the graph is not continuous at that location, then we can't talk about it increasing or decreasing at that location. Yeah.
So it's a point on your number line.
Right. It would be a point on your number line to mark a location where it might be changing. Yeah. Okay. Trig.
Oh, great.
Oh, wait. You guys just cringe at trig.
I know.
I don't know. Trig is so beautiful. It's a wonderful, wonderful thing.
On the rest of these notes,
Yes.
all the X's were changed into some weird Chinese word.
Yeah, you know, that happens every now and then, and I don't even know how that's possible at all, because it doesn't probably, I'll bet you that at least 75% of your class have notes that look just like mine, and yours printed out weird this time. It's weird stuff, yeah. So just fix it as we're going, Chad, and here's why I say I don't even know how it's possible. These are PDFs, and a PDF is supposed to be like taking a picture.
Yeah.
And that's why I post them in PDF form, and it does
It
stuff
looks
weird
like that until I print it, and then once I print it, it's all good.
It doesn't even, like, I don't get it. Yeah.
I didn't even notice it.
Yeah, well, and it may have looked just fine on yours, Fallon. Yeah.
I don't know, I printed mine all
Okay.
along.
Focus for me, guys. We're going to do one more, okay? Number 2, identify open intervals for the functions increasing, decreasing. Same directions, okay? Same directions. So what we're going to be doing is we're going to be doing the derivative, right? And in the derivative on this one will involve a chain rule. Yes? Some of you had ones like this. In fact, all of you had one like this on your test, and some of you forgot the chain rule as you were looking at this part of it. This is a chain rule because what this is it's really the cosine of x quantity squared. That's what you really have here. All right, so as we're looking at the chain rule on this one, what am I going to do? 2 will come down, cosine of x, technically to the 1, which is not very interesting, and then times, negative sine of x. The derivative of cosine is negative sine of x. And then I have the cosine part afterwards. What's the derivative of cosine? Negative sine, so this will be plus sine. Fantastic. And if I clean it up just a touch by moving the negative in front, this is negative 2 cosine x sine x plus sine x.
That looks a lot like it.
Okay. It does, and there's probably ways that you could manipulate and use it, but it's not really necessary for what we're working with here. Yeah. All right. What did we do after we found the derivative over here?
Set it equal to 0.
We set it equal to 0. And on that one, we were able to move things to the right and to the left and cross multiply because we had denominators, right? I don't have denominators here, correct? So I don't want to separate the two pieces of the addition and subtraction here on different sides of the equation. That would not be helpful. What is helpful is factoring. Very good, Bryson. So what can I factor out that they have in common? A sine of x. So if I factor out sine x, What's left from the first piece?
Negative 2 cosine plus 1.
And then plus 1 from the second piece. Excellent. Yeah. Okay, so far so good?
So you just find where sine is equal to 0.
We will find where sine of x is equal to 0. We'll also find where the other piece is equal to 0. We're going to do both of them.
Well,
Yeah.
if it's multiplied, like, anywhere where sine of x equals 0 is going to make that whole quantity 0, right?
You're absolutely correct. But also, anywhere that negative 2 cosine of x plus 1 equals 0 will also make the whole thing equal 0.
You're right.
Yeah. So we have to solve both of them. The first one's the friendlier one because it's just sine x equal to 0. So you need to be thinking, now notice, I didn't make a mention of it, I should have. Do you notice this one already gave you an interval to start with? It's because otherwise we would have these sort of like repeating processes over and over again because sine and cosine are cyclic, right? So they're actually focusing on one interval of the unit circle. Okay, so keep that in mind. We only have to worry about the unit circle. So where on the unit circle are sine values equal to 0?
0, pi, 2 pi.
0, pi, and 2 pi. And actually, 2 pi and pi are interval endpoints, right, that we were looking at. So the only new piece of information I'm getting is the pi.
Do we have to put the 0 and 2 pi?
You don't have to. No.
We always divide it up into two separate pieces when something.
If it's factored, you'll divide all the factors up into individual pieces, whether it's sines and cosines or whether it's polynomials. Yes. And in fact, we didn't do it this way, but this one could have been done as well from a factoring standpoint if you'd gotten to this point and you moved them onto the same side. This one also would factor as x minus 2x plus 2. And you would have gotten 2 and negative 2. Okay, so there's going to be places where you're going to end up with factors that are polynomials as well. All right, the next piece, I'm going to move my 1 and divide by my negative 2. So the cosine of x will equal what? 1/2. That requires a little bit more thinking on the unit circle part than the zeros, doesn't it? Okay, so cosine, let's start with quadrants. Which quadrants is cosine positive?
1 and 2 or 4.
1 and 4. Fantastic. We're halfway there. Well, maybe not halfway, but we're partway there. We're in the right quadrants. Yeah.
We didn't use the special triangle.
You can if you'd like. Yeah, that's a possibility. For most people, if they've memorized the unit circle, that's going to be quicker. But if you want to do it with triangles, more power to you. Unit circle then, cosine values of 1/2. Do you know where they are?
Pi over 3 is 1.
Is it pi over 3 or is it pi over 6? Because I'm hearing both.
Pi over 6 is for sine.
Okay, yeah, it is pi over 3. You're like, oh man, okay. So here's how I remember. Let me show you how I remember. These are our two options, is these two, roughly angle measurements, right?
Yes.
Sine is y values and cosine is x values,
Yes.
correct? Which of these two has the smaller x value? The one on the top or the one on the right-hand side?
Top.
The one on the top. This x value is smaller, and 1/2 is the smaller of the x values, 1/2 and square root 3 over 2. That's how I remember it. I've seen it before, but I want to make sure we can get through the rest of this particular problem before the end of class. So you can show me after class, okay? There's one more down here.
7
Which is that one? 5 pi over 3 is correct. Okay. So there are two additional locations. So we've got these two
Yes.
and this one. And I know that I don't need to go anywhere beyond 0 and 2 pi. So I'm not even testing on the outside of those. Those are not necessary. I do need to make sure I get these in order. So which one will come first of my three values?
Pi over
Pi over 3. What's next?
pi.
And then 5 pi over 3. Now, we're going to use a calculator to plug these in. So I have no interest in using pi over anything values, okay? Pi over 3 is about the value 1 because pi is about 3. Agreed? So when I'm looking at this, I'm looking at this and thinking, I'm testing 0.5. It's 1/2, okay? This value, pi over 3, is about 1. Pi is about 3, so I'm going to test 2. Pi is about 3, 5 pi over 3. Man, we're getting awfully close to the number 6. I mean, 2 pi over 6, 2 pi is 6. So I think probably 4 will work here. And I know 6 is smaller than 2 pi, just barely. So those are the ones I'm going to test. If you want to test different ones, that's great. Where will we test these? In the derivative. So we're testing f prime of 0.5, sorry, f prime of 2, f prime of 4, and f prime of 6. You do not have to show me the points that you select. Nope, you don't. But you do need to write down the positives and the negatives or the lines that show increasing or decreasing, some kind of indication of what you're seeing happen as a result. All right, so we're going to put the derivative in here, which was negative 2 cosine x sine x plus sine of x. Be careful with your parentheses. If you open an interval for x, you close it. We're almost done. I'm sorry, we're running just a little bit behind today. Make sure you're in radians. I am. And we're going to put in 0.5, 2, 4, and 6, which gives me negative, positive, negative, and positive. I will assume you can confirm that by your graph of yourself, not the graph of the derivative, the graph of the original. But then the answer to the question is where is it decreasing and where is it increasing? So this is decreasing from 0 to pi over 3. Union, so I like pictures. Decreasing, increasing, decreasing, increasing. Union pi to 5 pi over 3.
I have a question.
Yes?
Do we not need like the brackets for some reason?
On the endpoints,
Uh-huh.
this one didn't have them. You see how the interval is actually between 0 and 2 pi, not including the
Yes.
endpoints? That's why.
So then would a 0 be a fixed point?
What do you mean a fixed point?
Like, it would be a 0 with a bracket because it's like,
Okay, but this says there is no bracket.
oh, okay.
Yeah, it's
Oh,
the actual
okay.
conditions that we were given. Exactly. It would have an equals to if they wanted a bracket on it. And then I have 5 pi over 3 to 2 pi. Okay. And we could graph that to verify that if we wanted to make sure that the original graph, not the derivative, but the original graph matched that.